Hello everyone, welcome to Recitation session week 11 for CEE222 Water Resources Engineering. This week we will have 6 different questions. And for the first 2 questions, we are actually using Excel spreadsheet. So let me get started with the text of the question. So first of all, in this question, you will need to review example problem 6.9 in your textbook. And here, in this example, water depths are recorded at critical diversion points located at distances of 188, 423, 748, and 1675 meter upstream of the dam. So in this example, depths were only found at locations 188 and 423. And we need to determine the depths of flow at other 2 diversion points, which are 748 and 1675. And we need to use standard step method and a spreadsheet program.
And water depths for these 2 distances are already calculated. So first distance is 188 and second one is 423. So these are these calculations. But we need to find water depths that corresponds to these distances from the upstream of them. So basically, we have 13 different columns. So we have downstream, we have upstream. So the question in the example says that the downstream depth is 2 meters. And we are taking this as the reference, which is the distance. So if we use this equation, since this is trapezoidal, we can calculate area as 12, for example. And for the velocity, we are going to use the continuity equation, which is Q over area. And also in column 7, we are going to find velocity hat, which is velocity square over 2g. And then we are going to use this equation, which is weighted parameters for trapezoidal. And for hydraulic radius, we are going to just divide area by perimeters. And after that, for the field 10, we are going to use this slope equation, which comes from n square v square over hydraulic radius to the power of 4 over 3. And we will just get the average slope for the upstream and downstream. And lastly, we are going to find head loss using the average slope times delta L, which is the distance between these 2 points, between downstream and upstream. And so since we took the downstream as reference and the upstream from the dam is 188, we are going to use 188 times this slope value, and it gives 0.1042 meters as the head loss. And before calculating this energy, we are using this distance as SO times length. Because we have a slope and we need to find the horizontal distance so that it is 0.188. So After we found the head loss, we can calculate the total head for downstream and also for upstream. So for example, to find this value, we are going to use downstream depth, which is 2. We have the elevation, which is 0. We have velocity head as 0.055344, 304. And finally, the head loss was 0.1042. So this gives us 2.159. And then we need to find the corresponding water depth for 188 meters distance in elevation. So here we are using trial and error methods. So for example, if we start with, let me show that. For example, the correct value is 1.91. So let's say if it was 1.8, this time we would get 2.061. Let's make it 1.85. We are getting closer. And once we will use 1.95, these values are indeed very close to each other. And then we are going to skip to the next distance, which is between 188 and 423. So let's use this row. So for 188, we calculated water depth as 1.91. So we just use this here. And now we need to find this value. So again, we are just repeating what we did. And this time we used this elevation as 0.188. We calculated the area, velocity head, the perimeter, height of the radius, slope, and then here we also know that the elevation should be 0.43423. And based on these values, we are calculating all of these area, velocity head. And finally, we can calculate the slope based on these values. And here we have this average slope. And from this average slope, we can get the head loss. So here we can see that these values are very close to each other. So for example, so actually these are given in the example so that we don't need to find this actually, but we need to find the water depth for the distance 748 and also for 1675. So this is section 3 and this is section 4. So for section 3, this time we will start with this depth because it is coming from this elevation. So if we write everything we have, and then if write everything we have for the upstream of this point. So this was actually upstream of this point. So the water depth was found as 182. And in the next section, which is 748, this will be downstream of this section, which will be 182. And also this time, the delta length, which is the distance from 223 to 748, it will be 325. So for example, if it was 0, of course, it gave errors. So let's say if it was 1 meter, we will have this difference. So let's try 1.5. We got closer, but we still need to find the correct value. So let's say 1.7. We got very close, but we still need to find the exact value. So if we say 1.74, these are almost equal. So we can say that the water depth for this section is 1.74. Similarly, we are gonna repeat this value, repeat this calculation. So this time we are using this as downstream, and we need to find the upstream, which will be the elevation, water depth at this elevation. So it is 1.66. So let's continue with this shape. So I'm going to use this shape to better explain what we found. So as I mentioned, the first depth just downstream of the first section is 2 meters. So first of all, we calculated the water depth at this section, which was found as 1.91. Then we needed to find water depth for the section, which is further than 23. Then for section 3, and finally the section 4. So we can see that we have a higher depth just upstream of the dam, but we have lower depth at this distance.
Second question, this time we are still using example problem 6.9. And in this question, water depths were found for 188 and 423. And also in this recitation session, in the first question, we used standard step method solution, and we yielded depths of these 4 depths for these 4 different upstream distances of the dam. So we calculated 191 for 188. We calculated 1.82 meters for 423 meters, 1.74 for 748, and 1.66 for 1,675 meters. And in this question, we need to use direct step method, and we are going to use a spreadsheet program again. And this time, we are going to find upstream distances using these depths, so that we can compare if these distances are same, if we use these same depths in a different method, which is direct step method. Finally, we will see how closely these distances compare with the standard step method prescribed in the original example problem, which is 6.9.
So as I mentioned in the question text, we are going to find upstream distances using depths that we found in the first question. So we had these water depths 191, 182, 174, and 166. And in this question, we are going to find corresponding distances. So if you remember, we had these distances like 188, 423, 748, and 1,675. And based on these distances, we were able to find water depths. And this time we have water depths, and we are going to find distance to them. So as always, we are going to do our calculations. These are actually all same with the first question. But here we will use a specific energy equation, which was given here. And this is for downstream, and this is for upstream. And again, we are calculating the slope. And this time we are going to find delta length, which is the difference in the length, difference in the distance between section 2 and 1. And to find that, you can use this equation. So here, for example, we have downstream energy, which is 2.055 minus 1.272. And we will divide this value by SO, which is the channel's bottom slope, which is 0.001, minus the average slope. So it will be the average of these two slopes. And this equation is going to give 185.7 meters. So we can actually say that this is 186 meters. And then we are going to go the second step. And we already know all of these depths. And based on these values, we can calculate delta length. So it is almost 239. And let me also do that. So if we sum this distance with the length of, with the value of the difference, and we are going to get 224. And let's continue with this section. So from this equation, we can actually get delta length as 322. And this was for 24. And if you sum this value with this one, we will get 746. And finally, we will do these calculations, and it is going to give 870 meters difference from this section. So let me do this again. And finally, we will have a distance difference from 746 plus 870, and it is going to give 1616. So these are distances when we use direct step methods. But if you remember from the previous question, we used standard step method, and for this method we had these distances like 188, 423, and so on. So here we can see they are actually very close to each other, like 2 meter here, 1 meter here. We have 2 meter difference, and we have a little bit more difference, which is almost 59 meter difference. So this shows that we calculated distances and corresponding depths using two different methods.
Okay, everyone, let's continue with question 3. This is 6.9.1. So in this question, we have an earthen channel, and it will be excavated into a silt clay soil with a max N value as 0.024, and the slope M is 3. The channel will have a bottom slope of 0.002, and it accommodate a design flow of 4.58 cubic meter per second. So we are going to ignore freeboard, and we need to design the channel section. This means that we are going to find width and depth of the channel. So to do that, we need to find some values such as area, perimeter or hydraulic radius, so that we can create some relationships between these equations, and we can get the size of the channel. So before we get started, we need to consider a flow condition, so that the channel will not be eroded under this design flow condition, which is 4.58 cubic meter per second. So the assumption is that channel will not erode if the average cross-section velocity in the channel doesn't exceed maximum permissible velocity. So this is actually a certain value. So you can check table 6.7 in your textbook. So in this table, you will see certain values for different channel types. So for this channel, St. Clair soil, the maximum velocity will be 1 meter per second. So knowing that, we can start calculations. So as I mentioned, we need these size related values. And to find all of these, we need to start from hydraulic radius, because there is a certain equation for that. And since we know all of these values, we can calculate hydraulic radius. Then we can find perimeters, then others, either size related values. So let me get started with hydraulic radius. So n is 0.024, velocity is 1. Since we are using metric units, we have 1 times we have 0.002 as the channel slope. And this is giving us 0.393 meters. So that we have calculated hydraulic radius. After that, we can get area because we already know the flow rate, which was given as 4.58. So the area is equal to Q over V max. So 4.58 over 1. Of course, it is 4.58 square meters. And another value will be perimeter, because if you remember from hydraulic radius is equal to A over P. So since we need to find perimeter, we can get P as A over R. So this means that we have 458 over 0.393, which is coming from here. And from this equation, the perimeter is 11.7 meters. So that we calculated all of these values, but what we actually need is the width of the channel and the depth of channel. And this is trapezoidal. And from table 6.1, you can see the equations for perimeter and area. So the area is B plus my, or m is 3, we can say 3y, and y, this is equal to 458, and p is equal to p plus 2y, 1 plus m square, or 3 square to the power of 0.5, and this was 11.7 meters. And here we have two equations and two unknowns, which are b and y. So solving these two equations together, we can calculate b as 8.87 meters and y as 0.55 meters. From here, we need to make sure that the Reynolds numbers will not be very close to critical value. And you can find this information in your textbook. So for example, we can satisfy this condition if the Freud number is not in the range of 0.8 to 0.8 to 1.2. So let's calculate the Freud number here. So for the Freud number, we need v, which is velocity, over gt, acceleration, and hydraulic depth. So right now we know velocity, we know the g, but we need to find hydraulic depth. So again, from table 6.1, you will see the hydraulic depth for trapezoidal. So d is a over t. A was 4.58, and for t we have b plus 2my equation. And since we already know b and y, we can get 8.87 plus 2 times 3 times 0.45. And this gives 4.58 over 11.6, which is 0.395. So for the Reynolds numbers, right now we have 1 as velocity. We have 9.81 plus, times 0.395. And this is giving 0.508. And since this is not in the range of 0.8 and 1.2, because these are very close to critical value, which is 1. So we say that this is okay, and we can use this width and depth values to satisfy these conditions. Now we are at question 4, 8.9.3. In this question, we need to determine the flow rate, and we have 6.5 feet to 6.5 feet concrete culvert. So if the headwater is limited to a depth of 13.3 feet above the inlet or culvert bottom. So let me write this information first. So we have headwater elevation as 13.3 feet. Another important information is the culvert has a square-edged entrance, and it has a 50 feet long with a slope of 1%. Assume that the outlet is not submerged, which means hydraulic operation category C. But once the flow rate is found, verify that it is not category B by checking normal depth. So first of all, to see the flow classifications, You can check your textbooks, page 231 and 33. So in this page, you will see information about these flow classifications. And you will also see this figure in this page, figure 8.16. So let me write a few things here. So here we have head water elevation. We have tail water elevation. So for example, in the question, it says we have head water elevation as 13.3 feet. And also in the question, it says we have classification C, which means we have submerged inlet, but we have free discharge. At the outlet. So in other words, this means that we have partially full pipe flow, or this is open channel flow. And you can see that in the shape better because it is colorful. So we have submerged inlet and we have free discharge outlet. And this is partially flow pipe, full pipe flow. So we have water here, but there's nothing here. So this is open channel. And in the question, it says that we need to verify that it will be not phase B. Or in other words, it will not be full pipe flow, as you can see here. So to do that, we need to satisfy some conditions. So to keep it in case C or flow classification C, the normal depth should be lower than barrel height. And when we say barrel height, it will be here. Okay, so let's continue with this information. So first of all, for classification C, and I think it was in page 333, the Q is calculated using orifice equation, which is CD A area to G hash to the power of 1 divided by 2. And here H is depth above culvert center. So Q will be equal to 0.6. And this is the coefficient for superior edge atoms. Area is superior 6.5 square times 2 gravitational acceleration times h. So to calculate the h, we can again see the shape. We can see the figure. So according to the equation, we have a barrel height as 6.5. So the total distance here is 13.3 feet, and we have 6.5 here, and it says that H is depth above culvert center. So center of culvert will be this middle point. So we need to find distance from the center of culvert to the water surface elevation. So below the center, we will have 6.5 over 2, which means that this area will be equal to 13.3 minus 6.5 over 2. So let me repeat that. We have 13.3 here, and we have 6.5 over 2 here, and we find this required distance. From here, we will get the flow rate as 6.645 CFS. And now we are going to check the normal depth. And using Manning's equation, we can calculate, using figure 6.4a, you will see a figure that gives the normal depth. So we will have a graph like this, and on the x-axis we have NQ over KM. So, and width 8 over 3. So based on this value, we will have another value on the y-axis, which is yn over b. So this gives, let's calculate 0.013, which is given for the concrete. We calculated Q, so it was 645. K is 1.49 for British units. The slope was 0.01. And the width is given as 6.5. And this gives 0.38. So for example, let's say it is here, and the corresponding yn over b, or in other words, normal depth over width will be 0.8. And here, the normal depth will be 6.5 times 0.8, which is 5.2 feet. And as I mentioned, the question wants us to find these values, and also we need to verify that it is not category B. So the difference here will be this one. For classification C, the normal depth should be lower than barrel height. For our case, this was 6.5, and this is 5.2 feet, as we calculated. But for case B, this time we will have opposite. So normal depth will be higher than barrel height. So we already verified that the normal depth is lower than barrel height, which means the flow classification is C, and the flow rate is 645. Let's continue with question 5, 8.9.4. So here, the city engineer is concerned about the damage to homes, which is upstream of a box culvert during the 100-year flood event, with a flow rate of 12.5 cubic meter per second. The size of the culvert is 2 meter to 2 meters, with a square edged entrance condition, and the length of the culvert is 15 meters. The bottom slope of the culvert is 2%. And according to backwater computations, the tailwater depth is 2.75 meters above the bottom of the culvert. And also the upstream water depth of 3 meters will cause a flood to homes. So in this question, we need to find if these homes are in danger of flooding, and also we need to determine the velocity of flow through the culvert. So first of all, we need to find the flow classification, because based on the flow classification, we will have different equations or different approaches. So here we have an important information, which is tailwater depth is 2.75, and we have barrel height, or the hydraulic diameter of the culvert, as 2 meters. So if you look at the previous question, we need to find TWE is higher than D. So it doesn't satisfy this condition. Also here, we don't have this condition. And here they are equal. So the only flow classification is class A. So here, as you can see, we have 2.75 and we have 2. So we can see that this flow classification is A. So we have 2.75 tailwater, and we have 2 meters barrel height or hydraulic diameter. And also, as it is clear from this figure, the high water elevation is equal to head loss plus tailwater elevation. And so, considering these conditions, we are going to find the velocity of flow, and we will see the danger of flow, danger of flood. So we need to use equation 8.18, which is given here. So from here, we need to find the hydraulic diameter, which is A over P. So we already know the area. It is 2 times 2. And for the perimeter, we need to find the weathered perimeter, which will be 2 times width plus height of the culvert. So it will be 4 over 8, or 0.5 meters. So we can think it as like this one. So the weathered perimeter is 8 meters. Okay, and now we can calculate the head loss. So the entrance loss is 0.5. We have 0.013 for concrete culvert. The length is 15. The hydraulic radius, so hydraulic radius is 0.5. Times 2 times 9.81 plus 1 times Q square, which is 12.5 over 2 times 981 times area, which is 4 and square. So this is giving 0.81 meter as the head loss. And also from, let me find the figure numbers. Figure 8.17. You will see that headwater elevation is equal to upstream depth plus bottom slope times length. And from there, YU plus SO was given as 2%, which is 0.02. The length was 15. So we are using this equation now. This is equal to tailwater, which was 2.75 plus 0.81 meters, which is the head loss. And from this figure, the depth at upstream will be 3.26 meters. So from here, we need to also find velocity, which is Q over area. So we calculated the velocity as requested. And we also need to find the danger for homes. And if we read the question again, it says the upstream water depth of 3 meters will begin to flood homes. So upstream depth is higher than 3 meters threshold water depth. This means homes are in danger during this flood event. Okay, we are at final question 6, and we need to determine the size of a circular channel, circle culvert. And it has a length of 200 feet, a slope of 0.10, and the flow rate is 88.2 CFS. Here, the important information is the outlet will be unsubmerged, but the inlet, which has a secure edged entrance, will be submerged with a headwater depth of 6.6 feet above the culvert. So since we should have outlet unsubmerged and inlet submerged, this can be two conditions. It can be either flow classification as B or C. And we can actually see that from this figure. So as the question says, the inlet is submerged, but the outlet is unsubmerged. So it is either B or C. So that we will try both of these flow classes, and then we will select between them. And here the headwater depth is 6.6 feet, and we have this hydraulic diameter. So for B, if we write energy balance, and if you also check page 334, example 8.5, it is very related to this question, so you can see more details. And also, as we used in previous question, like here, the the headwater will be equal to upstream depth plus slope times length, and it will be equal to hydraulic diameter plus the head loss. Is like similar to this equation. So the upstream depth is 6.6, and we have 0.1 slope and 200 feet length. And this is equal to d plus head loss. And also from equation 8.18, you will see this head loss equation. But this equation is actually for SI units, and this is for heritage units. So you are going to add this 2.22. So if we write everything we have 0.5 plus and 0.024 for the Manix N value. And this is because we have metal culvert. The length is 200. We have 220. The height of the grade is d over 4. We have 2g plus 1. And we have 88.2 square, square, d and d to the power of 4. And since we have these two equations, we can solve them together. And from 1 and 2, the d is 0.75 feet, which is hydraulic diameter. So this is the condition where we have full pipe flow. For class C, which is partially full flow or open channel flow, we are going to use different equations. So if you remember, we use orifice equation, which is here is equal to CD area and to G hash 1, 2. The H is the distance from the center of culvert, and it is 6.6 minus d over 2, and it is coming from here. This is the center of culvert. We have 6.6 over 2. So the distance from this culvert to here, 6.6 minus d over 2. So from this equation, 88.2 is equal to, coefficient is 0.6. The area is d square over 4 times 2, 32.2 times 6.6 d over 2 square root. And from this equation, the d is 3.25 feet. And this is for if we assume the flow classification is C. So here, the general approach is selecting larger diameter to be on the conservative side. So that we are proceeding with this diameter, which is 3.25 feet.